So today we are supposed to move on to phase modulation mechanisms, starting with optical Kerr effect. But since we spent so much effort on Tuesday about amplitude modulation, so a simple review. Do you still remember the dynamic gain and dynamic loss response in the presence of an input show pulse? If you have an input pulse, do you still remember what would be the loss as a function of time? And what would be the gain as a function of time? Do you remember the shape of the curve? So can you draw virtually? If I have a fast Sechenov absorber for a Gaussian-like pulse, what is the shape of your loss curve? Similar, right? If I have a slow Sechenov absorber, what would be the shape? Good, precisely. It's a monotonically decreasing curve during the passage of the pulse, but after the pulse, the loss gradually recovers to the initial level. Okay, and the gain response is similar to slow Sechenov absorber. Okay, the only difference is the time constant would be modified because of the pump in the case of gain media. Okay, good. So that should be all you need to know. Just several shapes of the curve. That should be sufficient. Now we are moving on to phase modulation. In this section, we will talk about optical Kerr effect. And from the optical Kerr effect, there are two mechanisms that would play important roles in Moore-locking. One is cell phase modulation in the time domain, basically. The other is Kerr lensing effect in the spatial domain, basically. Okay, so one in time domain, the other in the spatial domain. But both of them originate from optical Kerr effect. Instead of just writing down the formula of optical Kerr effect, which is very easy, index change equals N2 coefficient times light intensity, I would like to show you why is that. Okay, so let's check the four-way mixing, the model of four-way mixing. If you have three sinusoidal plane waves at frequencies of omega 1, 2, 3, and send them into a nonlinear medium with chi-3 coefficient. Okay, chi-3 means third-order nonlinearity. Okay, basically all the materials have some third-order nonlinearity, more or less. Okay, and when these three waves interact with each other inside the chi-3 medium, what would happen? It's possible we can generate a new frequency component at omega 4. Okay, and the electric field of each of the sinusoidal plane waves can be formulated in this way. Okay, E sub I means 1, 2, 3, 4. You have 4 frequencies, right? Is equal to real part of big E sub I of Z. We will check what does this mean later. Times exponential to the J times omega IT minus KIZ. Apparently, the later term represents the carrier term, right? It's a standard sinusoidal plane wave carrier term. So the big E sub I should be the phasor, right? Phasor times carrier. After real part, you got the real electric field, right? But the difference is now your phasor is not a constant. It's not a constant complex number. It's a complex function of Z, because now inside the medium, all the frequency components should change with propagation distance, right? Simply imagine that initially maybe the three input waves are stronger, so it has larger phasor. But when they interact with each other, transferring some energy to the new frequency component at omega 4, all these three amplitudes will decay with Z. On the other hand, the phasor of new frequency omega 4 will increase from 0 to some value. So these phasors are no longer constant. They should be some functions of Z. And our purpose is solving these four functions as function of Z. Okay? Then we assume the nonlinear interaction is not too strong. That means all the phasors should change slightly, at least in one wavelength range. Okay, so you can propagate with Z, but within one wavelength, the wavelength is quite short, in the order of micron usually. If we assume the percentage of change of the phasor is quite small, then we can simplify the mathematical model. Okay? Say the new frequency component's phasor E sub 4 at frequency omega 4 equals omega 1 minus omega 2 plus omega 3. Okay? Then this new frequency component can be driven by the nonlinear polarization proportional to the product of three input phasors, E1, E2 star, and E3, okay, because of the chi-3 nonlinearity. Okay. Then what would be the corresponding equation? It's like this. The spatial derivative of the phasor is roughly equal to some constant times the chi-3 nonlinearity times the mutual product of the three driving fields, okay, E1, E2 star, E3. But we still need to multiply with an extra term, e to the minus j times delta k times z, where what is delta k? It's equal to k4 minus k1 plus k2 minus k3. The difference between wave numbers. So it denotes the wave vector mismatch, basically. So forget about the mathematics. Let's look at four-way mixing more carefully. So if you have three input waves and one extra wave as the output, what would be the corresponding energy diagram? Remember, energy has to be conserved, right? The 4 photons, the energy should be conserved. So what would be the energy diagram? There are more than one possibilities. For example, it could be like this. Okay. Combining three input photons, then emitting one output photon. Looks like some frequency generation. But this time, there are three input fields instead of two. So we need chi-3 instead of chi-2 nonlinearity. Okay, so this is just one possibility. There are other possibilities, such as omega 1 up, omega 2 up, but this time omega 3 down, omega 4 down. Okay? And the energy is still conserved, but of course, it's no longer some frequency generation. Okay? So general four-way mixing is quite diverse. You have many different possibilities. And the lower half talk about one spatial case. Omega 4 equals omega 1 minus omega 2 plus omega 3. So it could be like this. Okay. Combining the input photons of omega 1 and omega 2 and emitting another 2 photons, omega 2 and omega 4. So we have this photon energy relation, and the delta K means the photon momentum relation. Momentum has to be conserved as well. But energy is automatically conserved. Momentum is not. That's why the delta K is not always 0. Actually, usually non-zero. You have to do something to make it 0. Okay? This is so-called energy and momentum conservations in nonlinear optics. Okay? And you can also try to figure out why the product of the 3 electric field phasors, you have one complex conjugate for omega 2. Okay? Because now your frequency with a minus sign, it's a downward arrow. So the corresponding phasor has to be equipped with one complex conjugate symbol. Okay. One question. What is the importance of delta K if you look at this governing differential equation? If you want to maximize E4, the amplitude of the output field, you prefer 0 delta K. So let's check what happens if delta K is truly 0. If delta K is truly 0, this term can be dropped, right? It's equal to 1. So you have a spatial derivative proportional to this one, but this one should be almost like a constant, right? If we assume the 3 input fields, initially the power is quite large. So they will not lose much power compared with the input. Then the product of the 3 terms should be roughly a constant, independent of z, roughly. Okay? If the conversion efficiency is low, it's true. Then everything is constant. So you have derivative equals some constant. Then what is the solution? It's very easy. Your solution should be a linear function of z, right? 你的微分如果是常数，你的解是什么？线性函数 okay? If you have a linear function for E4, you have gradually increasing amplitude. That is what we desire in terms of energy conservation, energy conversion, right? But if delta K is non-zero, so you can imagine starting with z equals 0, your input, what is the value of this term? Is equal to 1, right? But when z increases to some extent, maybe this term can be minus 1 if the phase is pi, right? So you have positive 1 or negative 1, and even more, you have something in between. So that means if you have positive 1, according to our previous analysis, you have a linearly increasing function as a solution. But if you have negative 1, you are supposed to have a linearly decreasing function, which is undesirable. And in general, you have more than positive 1, negative 1. You have everything. So you can imagine the energy actually transfer back and forth among all the 4 frequencies. So you cannot have the maximum output if your delta K is non-zero. So that's the importance of making delta K 0 in practice. Then we think about the spatial case, degenerate four-way mixing. Okay? So if we have only one input wave, then I have only one input frequency, omega 1. Okay? Can we still borrow the model of four-way mixing? The answer is yes. You just replace omega 2, 3, 4 by omega 1. Okay? And your K2, K3, K4, your omega 2, omega 3 is replaced by omega 1. Your K2, K3 is replaced by K1, and the E2, E3 is replaced by E1. Okay? Then, based on this energy diagram, you can easily identify the new frequency omega 4 is still equal to omega 1. So no new frequency at all, right? In this special case, degenerate four-way mixing. You have just one input frequency, and you have only one output frequency. No new frequency is created. Then you should feel very boring. Then what's new compared with linear optics? Okay, that's the point. We should see what happens later. In this special case, we can rewrite the governing ordinary differential equation in the previous page by the replacements, okay, shown here. Then this is what we have, okay? And if you pay attention to omega over c, you should be able to identify that this is equal to the wave number in vacuum, right? So I use a new symbol K0 in place of omega 1 over c. Besides, E1 times E1 star should be E1 absolute square, right? So it's shown here. So the differential equation is simplified to this one, okay? And how about the wave vector mismatch, delta k? We just understood the importance of 0 delta k. Let's check this special case. The formula of delta k, but by substituting k2, k3 equals k1, you got this. And it's always 0. That means phase match is automatically satisfied without doing anything. Okay? And it's a big advantage because usually delta k is non-zero because of the material dispersion. Different frequencies correspond to different refractive index. In that case, delta k is usually non-zero. But in this special case, degenerate four-way mixing, since there is only one frequency involved, so dispersion is no longer a problem. And you have always 0 delta k. It means the following thing will happen almost universally. Without doing anything, this will happen. The Kerr effect will happen. Okay. Given we have a differential equation, the next thing is try to find the solution. So let's consider an easier example. Say for a plane wave at frequency omega 1 propagating along positive z in a linear medium without any nonlinearity, and the medium has an index n, then we already know the electric field phasor E1 of z should be proportional to e to the minus j k times z, and the k equals index n times wave number in vacuum, k0, right? It's well understood. Then the corresponding differential equation and the solution are like this. This is the first order differential equation, and the solution should be like this, e to the minus j nk0z. Now, let's compare our equation. For the signal plane wave at frequency omega 1, but due to degenerate four-way mixing inside a nonlinear Cauchy medium. Okay, now we have nonlinearity. According to the previous slide, the governing equation looks like this. But this is very similar to the governing equation about linear optics. Okay? As long as you can replace this one by a number, say n sub nl, nonlinear index. Okay? And of course, nonlinear index is equal to Cauchy constant over 2n1 times E1 absolute square. Okay, by comparing the coefficients, you can know that. Then, in the previous example, if you have this differential equation, you have a simple solution like this. Now, the corresponding differential equation is almost the same as the previous one, except for the previous index n now is replaced by a nonlinear index n sub nl. Everything else is the same. So we are supposed to have a solution like this. E to the minus j nonlinear index times k0 times d. Just like this, except for a simple replacement. Okay? If it is okay, then you can further figure out the meaning of nonlinear index, right? The nonlinear index is the index change due to the Cauchy nonlinearity. Okay? Without Cauchy, this term should be 0. Just look at the formula. When Cauchy equals 0, you have no nonlinear index. Okay? Because of the presence of Cauchy, now we have a nonlinear index. Actually, not index, absolute index, but index change. An extra index due to the Cauchy nonlinearity. Okay? And we also know there is a linear relation between E1 absolute square and the light intensity I. Eta means wave impedance, as we introduced in lesson 1. So you can equalize nonlinear index as some n2 coefficient times the light intensity. Okay? So now I have shown you why there is optical curve effect, why the index change equals n2 coefficient times light intensity I. The underlying physics is degenerate forward mixing. And since delta k is always 0, this phenomenon is universal. It always happens. You don't have to do any fast matching engineering. It just happens. Okay.